testing hypotheses, we want to have a concrete way of knowing when we need to reject the null hypothesis and when we don't. And this we do through p-values. So let's talk about test statistics first. So a test statistic is simply some number that we're calculating from our sample data, and we are looking at how far our data for that sample diverges from what we would expect if the null hypothesis H0 were true. Okay, if our test statistic is unusually large or unusually small, so unusually far away from what we'd expect, then that shows that the data that we have is not consistent with the null hypothesis. Now, specifically with that test statistic, we compute what's called the p-value. Okay, so that is the p-value is the probability, assuming that the null hypothesis is true, that the test statistics would take a value as extreme or more extreme than actually observed. And if we have a very, very small p-value, that means that there's a very small probability that we'd have a test statistic so extreme. And so the smaller the p-value, the stronger the evidence against the null hypothesis. Let's look at an example. So the study of sweetness loss, the first thing that we looked at for this chapter. The hypotheses are these. The null hypothesis is that mu equals 0. Okay, we saying that there's no sweetness loss, there's no difference in the cola from at first to a month later after it had been stored. Okay. The alternative hypothesis, the thing looking for evidence for, is that the cola lost its sweetness over time. So the sweetness loss score average we would expect to be positive. Okay. We computed that our mean was 0.3 for those 10 tasters. We also computed our z-score for that. Okay, we had z equals, and I'll just remind you, we had z equals 0.3 minus 0 over the 1 over square root of 10. Okay, and this gave us about 0.949. Okay, all right, so now I'm going to show you the p-value visually. Okay, this statistic here, our mean was at 0, and we got our 0.3. Okay, we were over here, and because we're doing a one-sided alternative hypothesis, we just want to know what's the probability that we get something as extreme or more extreme in that direction. That's the definition of the p-value. What's the probability of an observation being as extreme or more extreme? So as extreme or more extreme is this entire region, okay, to the right of that, because this is a right-sided, a right, what we call a right-tailed test. So we're just looking for this area right here. Well, we know how to get that area. We've got a normal distribution here. Well, we know how to get that. We can use our table with our z-score, or we can use our I'm going to go ahead and use Excel and go ahead and type this in. We've got norm.dist. And it's standardized, so .s.dist. And that 0.949. And cumulative, that's going to give us the area to the left. And so I'm going to go ahead and do 1 minus that to get the area to the right. Okay, and so we get our area here of 0.17. So this is 0.17. And that is our p-value. Okay, and what this is telling us is that there is a 17% chance that we end up with a simple random sample of 10 tasters that end up with a mean taste loss score of 0.3 if the mean is actually 0. So even if the cola has not lost any taste, there's a 17% chance that we'd end up with this sample mean of 0.3. That is not a very low p-value, and so so that is what tells us that we don't really have strong evidence against the null hypothesis. Let's look at the other, the job satisfaction example. The study of job satisfaction in that previous example has the null hypothesis of mu equals 0, no difference in job satisfaction between the self-paced and fixed-paced. And the alternative hypothesis, we were just wanted to know, is there a difference? We didn't care which side. So suppose that we know that differences in job satisfaction scores, okay, in the population of all workers follow a normal distribution with a standard deviation of sigma equals 6. So then we could go through and say we've got this normal distribution, okay, and our assumption, of course, is that our peak is at 0, okay? And then we could compute our z-score for whatever. Now, I'm just going to assume for now that the data gives us a mean score of 17 for our difference, okay? And we'd like to know, and I'll say that our sample size was size 18. We got 18 workers, and the mean job satisfaction score was 17, okay? And this was the mean difference in job satisfaction. So we'd like to know how significant this is here. And so we compute our z-score. We have a normal distribution with a mean of assuming 0, and the standard deviation would be sigma over the square root of n. Okay? And so we can compute our z-score for the 17. So we have 17 minus 0 over the standard deviation for the sampling distribution, 60 over root. Let's go ahead and plug that in to Excel here. So 17 over 60. Oh, that's, oops. Fix that parentheses. 60 over the square root of 18. Okay, and so we've got a 1.2 here for our z-score. And so about 1.2. And so we're over here, but this is a two-sided test. So we want to know what's the probability that we end up with something as extreme or more extreme than this observation. So we do both sides. So we actually look at the area to the right of 1.2, and we go to the other side of our mean and say over at negative 1.2, the area to the left of that. Okay, so we're going to get the area, and I'm actually going to do that one first. The area to the left of negative 1.2. I'm just going to multiply it by 2 because I've got symmetry here. So let's go ahead and do that in Excel. So that a normal.s.dist and negative 1.2. And that's the area to the left. And then we'll multiply that by 2 times that number. And that is our p-value, okay, 0.2301. And I rounded at some point, so that could be a little bit off. But that's the general idea. So our p-value is about 0.23. P-value equals about 0.23. Well, this is not a very small number, okay? And there's a 23% chance of something this extreme if the mean actually is 0. And so we haven't really found strong evidence against that assumption. And so we don't reject our null hypothesis.